What's going on, everyone? Welcome back. Moving on to the next video, we're now going to do an example on hypothesis testing. And as you can see, there's a lot written out on the board. This is a big example. So if you don't feel like writing all this out, there are lecture notes that you could print out where this is already typed out for you. If you're on my site, the lecture notes are at the beginning of the chapter. If you're watching this on YouTube, there's a link in the description box that will forward you to the lecture notes so you could print those out for convenience. So let's see what's going on here. We got a 20-ounce bottle of Gatorade is supposed to have 36 grams of sugar. The grams of sugar in all bottles is assumed to be normally distributed with a standard deviation of 0.6 grams. A manager wants to test whether the Gatorade in his factory is being produced correctly with the right amount of sugar with a statistical significance of 5%. He takes 42 bottles off the conveyor belt and their sample mean is 35.83 grams and their standard deviation is 0.8 grams. What does he conclude? So to do this hypothesis test, I'm actually going to do it in two ways. I'm going to do it manually, and then at the end I'm going to do it with the calculator as well. I think it's better to start off manually so you could kind of visually see how everything works, and then explaining the calculator is more of a breeze versus doing it the other way. So when I get a question like this, first thing I like to look for is what's my null hypothesis and what's my alternative hypothesis. Because depending on these, it's also going to tell us, are we dealing with a two-tailed test or a one-tailed test? Remember, the null and the alternative, they have different formats for two-tailed, left-tailed, right-tailed. So notice we're dealing with grams of sugar in a Gatorade bottle, and each 20-ounce bottle is assumed to have 36 grams of sugar. And a manager in a factory wants to see whether that is so in his factory, whether the production is being done correctly. So what is the manager looking for in this case? Notice that he's not too concerned with the difference in this mean going in a particular direction. And what I mean by that is he wants to know whether there is potentially too much sugar being put in each bottle or too little sugar. So he cares about both directions. And so what he's testing for is whether that mean is different than 36. And so the null hypothesis is equal to 36. And when the null and the alternative hypothesis is in this kind of format, as we discussed in that one-tailed versus two-tailed test video, when you got the equal sign, the non-equal sign, you're dealing with a two-tailed test, right? The manager wants to know, is there too much sugar or is there too little sugar? He cares about both directions, so there's going to be two rejection regions when we're dealing with this question. And so that's a good start already. So I already know we're dealing with a two-tailed test. And I got my null hypothesis, I got my alternative hypothesis that correctly relates to this scenario. Next thing I like to do is write out what I am given. So notice, let's go through these sentences. The grams of sugar in all bottles is assumed to be normally distributed with a standard deviation of 0.6 grams. So when they give you this, they're talking about the population of all bottles in the whole Gatorade company, right? All 20-ounce bottles. And so notice that we're given the population standard deviation in this case. So that's good information because, like the previous video, we know because this is given, we're going to be dealing with a z-test, right, to do this hypothesis testing here. And then let's keep reading. So manager wants to test whether the Gatorade in his factory is being produced correctly with the right amount of sugar with a statistical significance of 5%. So remember, significance is given by the alpha symbol and it's 5%. Or you could put it in decimals, 0.05. And if we know the statistical significance, we know the confidence percentage, or the confidence coefficient, it's always 1 minus the alpha, right? Or if you're dealing with percentages, 100% minus the statistical significance, and that's basically 95% in this case, or 0.95 if you want to deal with decimals. Right, so that's good. He takes 42 bottles off the conveyor belt. That's the sample size. He's looking at 42 bottles, so N is 42. Their sample mean, let's, like confidence intervals, let's represent that with X bar, so 35.83 grams. That's the sample mean of the 42 bottles. And their standard deviation, let's do S bar, is 0.8 grams. So that's the sample standard deviation. Notice that the sample standard deviation and the population standard deviation, sometimes they'll be given, both will be given in a question. You got to be able to differentiate both. And that's pretty much the information we are working with for this hypothesis test. So given our information, we already know the null and alternative hypothesis. We can now get into the technical aspects of this hypothesis test. So the next step, what I like to look for is what the critical values are going to be. And because we know this is a two-tailed test, then we know there's going to be two critical values. But if it was a one-tailed, it would only be one critical value we'd be looking for. And the critical values, finding these, depends on three things. It's going to depend on your significance level, which we're given, it's 5%, or your confidence percentage as well. Notice that both of these are related. Once you have one, you have the other as well. But I'm just going to keep it as significance here. But you could write significance or confidence percentage if you want. It depends on your significance level. What else does it depend on? It depends on whether it's a two-tailed versus one-tailed test. Right? We know in our case we're dealing with a two-tailed test. There's going to be two critical values, two rejection regions. But if it's a one-tailed test, you're only going to have one critical value. And it could be on the left side if it's a left-tailed test. It could be on the right side if it's a right-tailed test. So the critical value is going to depend on that as well. And then what else does it depend on? The distribution. That you are using. And notice in this case, because we are given the population standard deviation, we're going to be doing a Z test, or we're going to be using the Z distribution. And so the way this is going to look is we're going to be looking at a Z distribution. That's where we're going to be doing the hypothesis test on. And there's going to be two critical values, here and here. Now, these here are going to be Z-scores on a standard Z distribution, where the mean is 0 and the standard deviation is 1. So I mentioned this in a previous video. What we got to do is we got to kind of take this information, like that mean being 36 and the sample mean, and we have to kind of convert it to standard Z-scores, where this mean is going to turn into a 0, right, on a standard Z distribution. And then we got to find these critical values here. And these critical values, because that confidence percentage is 95, basically all of this, which is the acceptance region, is 95%. And then these here, the rejection regions, this is going to be 2.5%. And this here is going to be 2.5%. It's basically, because it's a two-tailed test, it's that significance level divided by 2, right? Exact same thing with confidence intervals that I was discussing before. And so these critical values, you just get either from the Z table or from the stats calculator. So hopefully by this point you're pretty comfortable with the Z table. Getting these here, you would look for the z-score where the area to the left of that z-score is 97.5%, right? Basically all of this, the 95 plus the 2.5. And this would be 1.96. And then it's perfectly symmetrical. So the negative value is negative 1.96. So those are the critical values. And so that test statistic, remember, basically taking the sample mean, converting it to a certain z-score. If that test statistic is going to be in between these critical values, then we're going to continue to accept the null or fail to reject the null. If it's going to be outside, then we're going to be rejecting the null. And a quick thing I want to mention is you could get the critical values with the calculator as well. So if you go to the stat menu, you hit F5 for distribution, and then you got to pick the distribution you're working with. So we're working with a Z distribution since we know the population standard deviation. So you would hit F1 there for the normal, and then F3 because we're finding a certain Z score. So we're finding the inverse of the normal. And then you would get to this input screen. Data would be variable. The tail is, there's actually multiple ways you could do this. Let's say that you want to get both of these z-scores here. Well, you would pick the centered area, right? So we're going to be working with this area that's centered, which is 95%. So you could put CNTR here, area 0.95, standard deviation is 1, and then the mean is 0 because we're working with a standard normal. Right, so notice that this standard deviation, this mean here, it's not the standard deviation and the mean in the scenario, in the question that we're given. Right, we got to convert everything to a standard normal. So we got to convert the critical values to a standard normal. We got to convert the test statistic to a standard normal as well, as I'm going to show you soon. And basically when you execute this, you would get these two values, negative 1.96, positive 1.96. Another way you can get this, for example, is you can put the tail here to be left. So you're looking at the area to the left of a certain z-score, and then this area you would put 0.975. And it would only give you this, the positive z-score, and then the negative one. It's perfectly symmetrical. So multiple ways to do this. I think inputting the tail to be centered is the best way. Right, so we got the critical values, which are on the Z distribution. Let's erase all of this here. And so this is good. We got our diagram. So we have, let's erase this here, we got our non-rejection region or our acceptance region where we're going to continue to accept the null. Or over here, we got our rejection. Reject the null. And so now the only thing that's left is to find out what is that test statistic. If you remember, I've mentioned this in a previous video. It's basically taking that sample mean and converting it. So you could put it on the distribution to see where it's going to fall. And in this case, we're doing a Z test. So we're going to be finding a Z. Let's call it a Z test statistic. And the general formula is basically the sample mean minus the population mean over the population standard deviation over the square root of n. That is the formula for a Z test statistic. So you may want to write that down right there. And so we would just input our info. So our sample mean, 35.83. Our population mean, 36. All over our population standard deviation, which is 0.6, over the square root of the sample size, which is 42. And so notice in this whole question, we haven't even used or touched this sample standard deviation yet. And the reason why, very similar to confidence intervals, is because we're given that population standard deviation, right? So we don't even use this. However, if we weren't given this, then we would have to use this, and it would be a t-test, and I'm going to go over that in a future example. But in this question, we are not using it. And so going back to this, if you input all of that in the calculator, you would end up getting negative 1.836. So that there is the test statistic in this case. And so what you do is you take that now, right? We converted it to a z-score, and you put it on your distribution. Where's negative 1.836? Well, that's going to be like over here, right? So this is where the test statistic is. You may want to put that these are critical values. So notice that the test statistic, it's in the acceptance region or the non-rejection region. And so we continue to accept the null hypothesis, or we fail to reject the null hypothesis. And so relating it to the question, to our scenario in the factory, basically what we would conclude is that there is not enough evidence that the bottles in the factory are being produced incorrectly. So there's not enough evidence that the bottles in the factory have something other than 36 grams of sugar, that there is a difference. And so we would continue to accept this null hypothesis as true, right? We don't reject it. Now, if we got something outside, so if we got like 2.01 or maybe negative 2.01, for example, for that test statistic, then that would mean that either we have evidence of this alternative hypothesis. We have evidence pointing towards that either there's going to be too much sugar being produced for each bottle or too little sugar being added in. But again, in our specific case, we don't have any evidence pointing towards that. Not enough evidence to conclude that there is a difference from 36. So the factory manager for now doesn't have to worry about anything. And finally, to finish off this example, let's show how we would do it in a stats calculator. So I made the inputs right here. So main menu, hit stat, F3, notice that says test for hypothesis test. And then we're going to be doing F1 because this is going to be Z. We're going to be doing a Z test, as we know, as we've mentioned throughout the example. And then you're going to hit F1 again because we're just dealing with one sample. We're going to be doing tests in future examples, future videos, where we're going to be testing two populations. So we're going to have two samples. In this case, we're only working with one sample. And so after all of this here, you're going to be taken to this input screen. And so the data you want to put as a variable. Now for this here, for this input, there's three different choices. Either doesn't equal, less than, or greater than. And I want to make a specific mention about this over here, that this input, it's based on the alternative hypothesis, not the null hypothesis. So when you're dealing with a two-tailed test, we know the alternative hypothesis is going to have this non-equal sign. So it's pretty easy to tell with a two-tailed test that that's going to be the correct input, like in this question. But when you're dealing with a one-tailed test, it could get a little more tricky because the null is going to have a less than sign, and so the alternative hypothesis is going to have a greater sign. Or the null can have a greater sign, the alternative hypothesis is going to have a less than sign, and that's when it could get a little bit more tricky. You got to know that this input, it's always based on the alternative hypothesis. So thought I would make a note. But in this case, we know it's going to be the non-equal input because that's what the alternative hypothesis in this case is. And then this here is the value of the null hypothesis. In this case, it's 36. Right, the number of grams of sugar that should be in each Gatorade bottle. And then this here is the population standard deviation, which is 0.6. This here is the sample mean, which is 35.83. And the sample size is 42. And after you've inputted all that and you execute, you're going to get this output right here in the calculator. So it's going to give you the alternative hypothesis. It's going to give you the z-score, right? Or the z-test statistic, which we got as well, negative 1.836. It's going to give you something called a p-value. I'm going to discuss that in a second. And then the sample mean, and then the sample size. So really what we're looking at is this over here. We can also look at the p-value. Again, I'm going to mention that in a second, but notice how this is the test statistic that we calculated before. And then from here, you would just compare where does that test statistic fall on the distribution. And yeah, so the critical values we got from a separate step, and then it falls in between, so we don't reject the null hypothesis. Okay, now what does that p-value mean? Now I'm going to actually do a video in the future discussing the p-value in more detail. For now, here's all you need to do. You got to just remember two rules. Basically, if that p-value is less than the significance level, then we reject the null. And if the p-value is greater than the significance level, then we fail to reject. So what was our significance level? If you remember in this question, our significance level was 5% or 0.05. And notice the p-value in this case is 0.0663. So which one of these scenarios is it? Well, the p-value is greater than the significance level. We fail to reject the null, which is the exact same conclusion that we came up with using that test statistic as well. So that's another way to look at it. It might be even an easier way to look at it. It's just I haven't gone into the p-value yet, what it actually is. So I wanted to focus more on this test statistic here and how it compares to the critical values. Basically, if you want me to give you a quick explanation of this p-value, the way it kind of intuitively works visually. So let's say that we're dealing, let's kind of forget about this example. Let's say we're dealing with a one-tailed test. So there's only going to be one critical value. It's just easier to show with a one-tailed test. And so notice that this whole area here is the significance level, right? And let's say that the significance level is 5%. Now, what the p-value is after we get the test statistic, let's say that the test statistic falls over here. So this here is the test statistic, whether that's on a z distribution or a t distribution. Let's say it just falls here. So it falls in the rejection region. So we're going to be rejecting the null. Basically what the p-value is this area over here, right? It's that. So from the test statistic and on. So this here, this area is the p-value. And so notice that this whole area is the significance, right? The rejection region, while this area that depends on the test statistic is the p-value. So notice if the p-value is less than the significance level, then we're going to reject the null, which makes sense because that p-value is kind of like within that significance area. Versus, let's say that the p-value is greater, like we got in this case. Well, if we have a critical value and then this here is the rejection region, right? Again, let's say that the significance is 5%. Then we get a test statistic here. Notice that the p-value is all of this, right? So notice that the p-value is greater than 5%. And so notice that it's not in that rejection region. That's why when that p-value is greater than the significance level, we fail to reject it. That's kind of how it works visually. So hopefully in future examples, even though we're not going to be talking about the p-value in too much detail over the next few videos, I'm going to talk about it in more detail in a future video, you can kind of know intuitively what is going on. Just basically remember these two rules, and the reason why is it works like that visually. Anyway, that's how you do hypothesis testing. So that's an example. We knew the population standard deviation, so we did a z-test. And we knew it was a two-tail test. So 2 critical values, 2 rejection regions, calculated that test statistic, and it was within the critical values, so we failed to reject the null.